Hi everyone, what's up? Welcome back to my tutorial channel. It's Daniela here, and today I'm going to talk about the Black Scholes Option Pricing models. In this first video, I'm going to discuss the first part, LOGNORMAL models. I'm going to give you an introduction to the LOGNORMAL models and how to calculate the probabilities, the percentiles, the mean variance, the conditional expectation of LOGNORMAL models on the stock prices. Alright, so first the LOGNORMAL models. Let's say a random variable y follows LOGNORMAL distribution with mean mu and variance sigma square. This is equivalent to natural log of y is a random variable that follow the normal distribution with mean mu and standard deviation sigma. So this is just a definition. We say y follows log normal distribution with mean mu and standard deviation sigma if the random variable natural log of y follows normal distribution with mean mu and standard deviation sigma. Now let's consider the cumulative probability density function. Capital Fy of y, this is the cumulative probability function of variable y. So this should be equal to probability that the random variable y is less than or equal to a value little y. And let's take natural log both sides in the inequality. We got this should be equal to probability that natural log of y is less than or equal to natural log of little y. And of course, since natural log of y is normally distributed, so we can use standardization to calculate this probability. So we got probability that natural log of y subtract mu over sigma is less than or equal to natural log of little y subtract mu over sigma. And the left hand side in the inequality is z, which is a standard normal distribution for a random variable. And the right hand side is notated by a little z representing for a value of random variable z. And this is phi of z. Remember in statistics, phi, the capital phi here represents the cumulative probability distribution of the standard normal distribution random variable. So z here follow the standard normal distribution. See that? And so we have figured out that f capital of y is equal to capital phi of z, where z is equal to natural log of y subtract mu over sigma. So now in order to find the density function, we basically take the fourth derivative of the cumulative probability function respect to variable y. So little f y of y is equal to d over dy of capital F of y, which is equal to d over dy of phi of z. Remember, phi of z is a function of z, so in order to work on this differentiation, we need to use chain rule. So we apply chain rule here. We got d over dz of phi of z times dz over dy. And d over dz of capital phi of z is just little phi of z. These are different, okay? This is capital phi, represent the cumulative probability function of the standard normal distribution. And the little phi here is the density function of the standard normal distribution. And dz over dy, look at here, z is natural of y minus mu over sigma. So when we differentiate z respect to y, we got 1 over y times sigma. That's why this one is equal to little phi of z over y sigma. And is equal to 1 over y sigma times with 1 over square root 2 pi e to the minus z squared half. Remember, little 5z is the density function of the standard normal distribution. So little 5z is 1 over square root 2 pi times e to the minus z squared over 2. Whereas z here is defined as natural log of y subtract mu over sigma. And the moments of the log normal random variables is expected value of y to the k is equal to exponential of mu times k plus sigma squared k squared over 2. Alright, so that is about log normal models. Here we need to, there are 3 things we need to pay attention here. First, y follow log normal distribution if natural log of y follow normal distribution. And the second thing is little f y of y is equal to 1 over y sigma times 1 over square root 2 pi e to the minus z squared over 2, where z is natural of y minus mu over sigma, and the moments expected value of yk. So these are the 3 core things that we need to pay attention in this slide. Alright, now how do we calculate the probability of a distribution of log normal? So let's consider this example. Let x be normally distributed with mean 0.5 and variance 0.5. Let y is equal to 0.5 e to the x. Compute the following. Probability that 0.51 less than y less than 0.8. Find a distribution for y and then recalculate the probability of both using the probability distribution of y. So here we see, first of all, I'm going to use normal distribution to calculate this probability. Then I'm going to derive the distribution for y and use the distribution of y to recalculate this probability. So first, let's look at the first step. Probability that 0.51 less than y less than 0.8. Here y is 0.5 times e to the x, so I basically substitute y into this formula. So we got probability that 0.51 less than 0.5 e to the x less than 0.8, and from here we solve for x. So we got probability that 0.0198 less than x less than 0.47. The number 0.0198 came from natural log of 0.51 over 0.5. You see that here, in order to solve for x, first we have to divide 0.5 and then take natural log, right? So we applied this process to 3 sides of this inequality. So we got natural log of 0.51 over 0.5 is 0.0198. And similar for the right hand side, we got natural log of 0.8 over 0.5 is 0.47. And then remember that x is normally distributed, so we need to use standardization to calculate this probability. So this step, the third equal sign, we use standardization. X here follows normal distribution with mean 0.5 and variance 0.5. That means the innovation is square root of 0.5. So we use standardization. So we got 0.0198 subtract 0.5 over square root of 0.5 is negative 0.679. And similar for the last number, we got 0.47 subtract 0.5 divided by square root of 0.5, we got negative 0.042, which is equal to 0.2347. And the distribution of y. So that was the first way to calculate the probability of this example. Now we are going to construct the distribution for y, then recalculate the probability using the probability distribution of y. Here we see that y is equal to 0.5 e to the x. So if we take natural log both sides, Remember, natural log function is the inverse function of exponential function. So that is the reason why we have to take natural log both sides. So we got natural log of y is equal to natural log of 0.5 plus x. And remember, x follow normal, and natural of 0.5 is a constant number. So of course, a normal random variable plus a constant is also normal. So we got natural of y follow normal distribution, where the mean is natural of 0.5 plus the mean of x, which is 0.5. And the variance here is just 0.5 because constant doesn't affect the variance. So we see that natural of y is normally distributed, right? So y should be log normal distributed with the same mean and mean elevation. Again, let me repeat this. You see that natural of y is a random variable that follow normal distribution. So y is a random variable that follows log normal distribution with the same mean and variance. So we got the using the last slide, we got the cumulative distribution function of y is capital F, y is equal to 5. Natural of y subtract natural of 0.5 subtract 0.5 over square root of 0.5. And now we can basically use this distribution to calculate the probability given. So here's the thing. Probability that 0.51 less than y less than 0.8 is equal to capital Fy 0.8 subtract capital Fy 0.51, because it's basically just probability that y less than 0.8 subtract probability that y less than 0.51. And just using this formula, we got capital Y of 0.8 is phi of natural log of 0.8 subtract natural of 0.5 subtract 0.5 over the square root of 0.5, which is phi of negative 0.042. And similar for the second term, we got phi of negative 0.679. And either use the z table or use calculator or software. We find out the answer is 0.2347. So we see that no matter what methods you approach this problem, you have the same answer. You see that the first solution we use normal distribution. The second solution we use the distribution of log normal distribution, and both methods use the same answer. You see that. Alright, so that is how we calculate the probability of log normal based distribution. Now let's look at the application to option pricing of log normal distribution. So log normal distribution has a very big application to option pricing for stocks, and it's called the Black Scholes model. There are two rules. There are two rules in the Black Scholes model. The first one is about the stock price distribution. Here we have two statements in the first rule. The time t price of the underlying asset ft follows a log normal distribution. So that means stock price should follow log normal distribution. The underlying assets either non-dividend paying or pay dividends continuously at a level proportional to its price. So we only apply it to the case when we have no dividend or dividend is paid continuously at the level which is proportional to the stock price. The second rule is about the economic environment. So here we got 4 main points. The first one, the continuously risk-free interest rate RF is constant and is the same as the borrowing rate and the lending rate. So you borrow and lend at the same rate, and also it should be the same with the risk-free interest rate. There is no transaction cost for any transaction, no taxes, no transaction costs, and you can purchase any units of the underlying assets. And the last one is there are no arbitrage opportunity. Remember, arbitrary opportunity we learned in the last lesson. So that is the application to option pricing. Here we need to know the two rules in the Black Scholes model. And now let's talk about how to apply it. The properties of returns. Here, let's say we consider the two different times of the stock price, time T1 and time T2. So let's say our T1, T2 is the continuous compounded rate return of stock S from time T1 to T2. So we got R T1, T2 is equal to natural FT2 over FT1, because if you look at the row model, we got S of T2 is equal to S of T1 times e to the R T1, T2. So from here, in order to solve for the rate of return R T1, T2, we basically take log natural log of FT2 over FT1. And the continuously compounded compounded returns are additive. For example, if we consider three different times, T0, T1, and T2, in the order that T0 less than T1 and less than T2. So we got R T0, T2 is equal to R T0, T1 plus R T1, T2. So that means they are additive. And it's very easy to prove it. Remember, by the formula we got R T0, T2 is just natural of FT2 over FT0, and it should be equal to natural of FT2 over FT1 plus natural FT1 over FT0. So that's why we said the continuously compounded returns are additive. Returns over two overlapping time periods are independent. So for example, we see here, let's say T1 is the point between T0 and T2. So the interval from T0 to T1 and the interval from T1 to T2 are non-overlapping. So the returns over these two time periods are independent. That's the main point. And this is one of the assumptions for the option pricing model. And the second assumption is about the mean and the variance. Here the mean and the variance of the rate of returns R T1 and T2 are proportional to T2 minus T1. In particular, we let mu of R is equal to alpha minus sigma minus alpha minus delta minus sigma squared over 2 times T2 subtract T1. And sigma squared of R is equal to sigma squared times T2 minus T1. Here, alpha is a stock expected rate return per annum. Delta is continuous dividend yield. Sigma is stock for totally annum. And R T1, T2 is normally distributed. R T1, T2 follow normal distribution with mu R and sigma R squared. By standardization, we got Z subtract mu over sigma follows standard normal distribution. So by notation, we can make a connection between the random variable R T1, T2 and the standard normal distribution random variable Z. We got R T1, T2 is equal to alpha minus sigma minus alpha minus mu delta minus sigma squared over 2 times T2 minus T1 plus sigma squared root T2 minus T1 Z. And here, if we consider different time from 0 to t instead of T1 to T2, then you see T2 subtract T1 should be just t. So that is a special case when we consider from the initial time to another time. Alright, so now let's look at the log normal property of the stock prices. Here we on the Black Scholes model, we got a time t stock price. When we consider from the initial time 0 to the time t, we got S of t, the stock price at time t is equal to the initial stock price S0 times e to the R 0t by the Grow model, where the rate of returns R0t follow normal distribution. Alpha minus delta minus sigma squared over 2 times t sigma squared t. it just similar by saying that the mean and the variance of this rate is proportional to the time. It is obviously that natural log of s of t is equal to s of 0 plus r0t. And because r0t is normally distributed, natural log of s0 is a constant. So obviously, natural log of s of t follow normal distribution. And by definition, since natural log of s of t follow normal distribution, so s of t follows normal distribution. And the mean and variance of the stock price here is for the expected value s of t, we got s naught times the exponential of alpha subtract delta subtract sigma squared over 2 plus sigma squared over 2 and t, and which is equal to s0 times exponential of alpha minus delta times t. And in order to derive it, it's very easy. We start with this line. We start with natural log s of t is equal to natural s0 plus r0t, where r0t follow normal distribution. Then we calculate the expected value and this variance for this. So the expected value of natural s of t is equal to natural of s0 plus alpha minus delta minus sigma squared over 2 times t. And from here we solve for expected value of s of t by taking exponential both sides. So that's how we derive the mean and the variance for the stock price. Now let's look at the stock price model under the Black Scholes framework. That means under the Black Scholes assumption. Under the Black Scholes framework, we consider the time t stock price follows log normal distribution. So s of t following log normal distribution would mean is natural of s naught plus alpha minus delta minus sigma squared over 2 times t, and the variance is sigma squared times t. So we got ft here is basically just s naught e to the r0t. Okay. And it's equal to s naught times with exponential of alpha minus delta minus sigma squared over 2 times t plus sigma squared t times z, which is how we make connection between the random variable s of t and the standard normal distribution random variable z. That where z here follows standard normal distribution. So we see that this is the relation between s of t and z. And of course, using this relation, we will be able to find the percentiles and also the probability of s of t using z. So let's say if we consider the percentiles of the stock price, the 100 percentiles of the stock price can be calculated by using the 100 p percentiles of the standard normal distribution. So here, basically like here, in order to find the 100 p percentile s of t, we first find the 100 p percentile of z and then plug into here. So we basically replace z on this formula with phi inverse of p. And the median of it is similar. For the median, it's basically just a 50, it's just like the 50 percentile of s of t. So we got p here is 0.5, we say p is 0.5. So phi inverse of p is just 0. Remember the median of the standard normal distribution is 0. So this term is cancelled out. That's why the median of the stock price is s0 times with exponential of alpha minus delta minus sigma squared over 2 times t. That's how we find the percentiles. Now let's look at the cumulative distribution of s of t. How do we derive it? We start with probability of the stock price s of t less than or equal to k. K here is a trial price, for example. In order to derive this probability, we have to take natural both sides. And the reason for it is, remember, natural of a log normal random variable is a normal random variables. And for any problem, if we can convert to normal distribution, it would be very easy to calculate. That's why we have to take natural log both sides to convert this problem to normal distribution. So probability that S of t is less than or equal to k is equal to probability that natural log S of t is less than natural log k. Remember that natural S of t follow normal distribution. With this is the mean and this is the variance. So by standardization, basically just use standardization, we got probability that natural S of t less than natural k is equal to probability that z less than natural of k minus natural of s0 minus alpha minus delta minus sigma square root 2 in the frequency times t over sigma square of t. It's just like we take the variable, we take the value, subtract mu over sigma, that's it. And since these follow standard normal distribution, so we can use the phi notation. So this probability is phi inverse of natural of k minus natural s0 minus alpha minus delta minus sigma square over 2 times t over sigma square of t. And I'm going to notate the whole thing in the frequency here by d hat. And you know what? Sometimes we consider the probability that S of t is greater than k as well. So I'm gonna do one more step here. That is, I notate d2 hat is equal to minus d. So phi inverse of d is phi inverse of minus d2 hat. And by using normal property of the property of normal cumulative distribution, we got this is 1 minus phi inverse of d2 hat, where d hat here is natural of k minus natural s0 minus alpha minus delta minus sigma square over 2 times t over sigma square of t. And d2 hat is here, it's just flip side, because it's just like the opposite with this. So we flip the side. We got natural s0 subtract natural k plus alpha minus delta minus sigma square over 2 times t over sigma square of t. And the reason for it is, remember, we sometimes need to calculate the other side of the probability that S of t is greater than k. Alright, so now let's consider the conditional expected prices. Here's two formulas we need to memorize. First, expected value of S of t, given that S of t is less than k, is equal to expected value of the stock price times with phi of minus d2 hat minus sigma square of t over phi of minus d2 hat, and is equal to expected value of S of t times phi of minus d1 hat over phi of minus d2 hat. And the opposite situation, expected value of the stock price given that S of t is greater than k is expected value of the stock price times with phi of the d1 hat over phi of d2 hat, where d1 here is natural s0 minus natural of k plus alpha minus delta plus sigma square over 2 times t over sigma square t. Here the only thing different between d1 hat and d2 hat is just right here. Here for d1 is plus right here before sigma square hat, and for d2 is minus. So there's a relation between d2, that is d1 hat is equal to d2 hat plus sigma square t. Here it should be d1 hat, okay? And the proof for it is just expected value of stock price S of t, given that stock price S of t is less than the trade price k, is equal to expected value of the stock price when the stock price is less than k over the probability that the stock price is less than k. And it's just expected value S of t times phi of minus d1 hat over phi of minus d2 hat. And similar for the second expected values. Alright, So that's it for today. Thanks so much for watching my video. I hope you guys enjoyed my video, and I will continue to talk about this topic because this is not the end of the topic. I still have to include some examples and concepts. So see you on the next video. Bye.